already discussed about first law of thermodynamics and H pathway and how to calculate the work for each thermodynamic pathway like isothermic, adiabatic, isobaric, as well as isometric or isochoric. Now, for starting from now, we will discuss how to integrate all of those systems inside a cycle. We call it this as thermodynamic cycle, which can work as heat engine as well as heat pump. So this is the basic idea from the second law of thermodynamics. There will be two different parts. The first one is heat engine, the second one is heat pump. This is the schematic diagram for heat engine. Let's say you have heat engine on the middle, and then you have heat source at a certain temperature, in this case T1. T1 will supply heat to heat engine. We denote this one as Q1, and the heat engine will release the additional unused energy in terms of heat. We denote this one as Q2. Actually, the idea of the heat engine to transform the energy from the heat into work. So that is the basic idea. Unfortunately, there will always be unused energy which will be released to the environment. That's why we put Q2 as the energy that should remove to the environment. In this case, heat sink with temperature denoted as T2. So basically, heat sink is the heat discharge into the environment. Don't forget, in this case, T1 is higher than T2. So the heat source has higher temperature compared with the environment as heat sink. Okay, so that's why there is a sentence that in bold. It is impossible for a heat engine to undergo a cyclical process, turning the incoming heat is this one, the Q1, into work without removing some of the heat to another system of lower temperature. So we will still use the first law of thermodynamics. Delta U is equal to Q plus W. But please be aware, we need to calculate for the whole cycle. We will discuss the details about this later on. And the one that we should understand in this system is there will be what's so called by efficiency, heat engine efficiency. So basically the output, that one is work divided by input. The input is heat supply from the heat source. So W by Q1. This W is net work generated by the cycle itself, by the whole machine. So later on we will see that work, this net work is basically work generated minus work consumed. So there will be a difference between work goes out with the work goes in. Okay. Now let's try the opposite one. Still using the basic principle of second law of thermodynamics. The idea of heat pump is similar with the analogy. Let's say we want to transfer water from lower elevation to higher elevation, because naturally water always flow from higher elevation to lower elevation. The same principle can be applied for heat. Naturally, heat will flow from higher temperature to lower temperature, but it is possible to transfer heat from lower temperature to higher temperature using what's so called by heat pump. So the idea is we want to transfer the heat from T2 to T1. This one is T1. We want to transfer the heat from heat source to heat absorption from T2 to T1, where T1 is higher than T2. It means we can transfer heat from lower temperature to higher temperature using additional energy. We use work that goes into the system called heat pump. Okay. In this case, there is no term of efficiency, because in terms of efficiency, the maximum value of efficiency should be 100% or 1.0. In this case, the term of efficiency is replaced by coefficient of performance, denoted by COP, coefficient of performance. If you see here, the coefficient of performance is the heat that transferred by the heat pump, Q2, divided by work in. So it is possible to have COP that higher than 1.0, higher than 100%. In fact, if you see from your refrigerator, some of the refrigerator spec, it was written the value of COP. You can check from your fridge or refrigerator. Sometimes it can be in the value of 5 or in fact 7. Okay. So heat engine versus heat pump. In heat engine, we can produce work from the heat. Yeah. On the other hand, for the heat pump, we can transfer the heat by putting work. Okay, up to this point, any question? Don't forget that we will always use the first law of thermodynamics, the law of energy conservation. Q1 is equal to work plus Q2. Okay. Now, this is the famous cycle from heat engine. We know this as Carnot cycle. The principle is the same as the previous one. We have heat source supplying heat to heat engine to produce work with unused energy that should be released to the environment, denoted by Q2. The heat can be released to the environment, in this case, released to heat container. There will be several cycle, thermodynamic cycle. The ideal one is Carnot cycle. What is the ideal case of Carnot cycle? Let's check one by one. The first one is isothermal heat absorption. From the first state to the second state, following isothermal pathway. that we already discussed on the previous class. Okay, this is PV diagram, pressure to volume diagram. Remember that isothermal curve is always much smoother compared with adiabatic pathway. So adiabatic is steeper. Now, when you have the first state to the second state, the isothermal will give an expansion effect. During this case, because the temperature remains the same, but there is a heat that can be absorbed to the system. In theory, it is not possible to have this condition. In isothermal process, the temperature that remains the same, but we can absorb the heat. So that's why this is the ideal case. Why Carnot give isothermal? Because it will give the highest efficiency for thermodynamic cycle. Okay. Now, the second one is from the second state to the third state. You can see adiabatic curve from 2 to 3. Because there is an increase in volume, we know that this one is adiabatic expansion. Remember, expansion means the system will produce work. The next point is from state 3 to state 4. Again, another isothermal process. The volume decreasing, the heat release. So that's why we put here as isothermal heat release. And the last step is from state 4 back to state 1. So it's a closed cycle. The process from state 4 to state 1 is adiabatic compression. It means the work goes into the system, okay, from the environment. So the system is not producing, instead consuming work. So we can have this working. Maybe some of you confused why the isothermal is not, the term of isothermal is not isothermal expansion, or the opposite one from 3 to 4 is not isothermal compression. Some of the book mention about that. But the case in this system is related with the heat transfer, not the work. That's why the term is not isothermal expansion or compression. Instead, they put isothermal heat absorption and isothermal heat release. Okay, once we denote everything in PV diagram, we understand the cycle, and we also follow this system. Please be aware that the cycle follow a clockwise. Later, when we discuss the opposite of this system, the heat pump, the cycle will follow counterclockwise. Okay, in this case, this is clockwise. The next one is related with the work. Remember, the efficiency is work, net work. So work netto, it means work out minus work in. So the work netto is work 1 minus work 2. This one should be minus. This one should be minus. Work netto is positive. So work out minus work in. So actually work 2 minus work 1, which equal to, sorry. This is my mistake. Sorry. Use the standard term. Work is equal to work in. Remember, all energy that goes into the system should be given a positive sign. So this one is work 1. How about work 2? Because moving out from the system, we should put minus sign like this. That's why there is a term work in minus work 1 minus work 2. How about the heat? Heat that is coming to the system is plus Q1. Heat released from the system is minus Q2. Why there is a minus sign here? Remember, delta U is equal to Q1 plus, Q plus W. Q plus W. Because of this closed cycle, delta U would be equal to 0. Remember, because the reason is because 1, 2, 3, 4, and return to 1. That's why delta U as state function, it should be equal to 0. Okay, so because of this, Q is equal to minus W. That's why the term here is equal to minus Q1 minus Q2. Okay, why we have to calculate based on this? The idea is we still follow the first law of thermodynamics and the second law of thermodynamics when we calculate the efficiency. Okay, so this one is simple, right? Just replace work with minus Q1 minus Q2. So this one you can replace with efficiency is equal to Q2 minus Q1 over Q1. So this one is equal to 1 minus Q2 over Q1. So it's the same. Okay, any question regarding with the Carnot cycle? Remember, this one is ideal case. Okay. Now a little bit about this characteristic. The term thermodynamic efficiency. For Carnot cycle, this is the highest compared to all other cycles. If we want to compare, for sure it should be operate in between the same operating temperature. In this case, T1 and T2. Efficiency can be reached very high when Q2 is equal to 0. It means 100%. In this case, it's impossible. Remember, if we want to have 100% efficiency, this value should be equal to 0. So 1 minus 0 is equal to 1. 100% efficiency. Why this one become impossible? Because the heat unuseful heat should be released to the environment. It's not possible to have 100% of heat converted into work. Okay, so the reversible process is achieved if the temperature of T1 is equal to the temperature of the working fluid. So we will discuss about working fluid when we see the diagram. It will be easier for you to understand. Similarly, for the B, when the heat receiver has a similar temperature with fluid when discharging heat. Okay, the reversible is the same. Now, fuel engine itself, the real one, is slightly different from this cycle. So Carnot process is really an ideal process. An example for petrol or gasoline motors as well as diesel motor. The engine is not following the same principle. Now let's discuss the real case of engine. Similar PV diagram. There is a certain sentence that is not right, but just follow this. Let's say the first one, it mentioned adiabatic compression. If you see this shape, let's say this is 0.1 and this one is 0.2. When you see this picture, this diagram, automatically you will say that one is isothermal curve instead of adiabatic. Okay, so it will be better if the picture is slightly steeper, and then straight up, increase again, and then straight down. People will understand this system much easier because of a different slope between isothermal and adiabatic. But let's assume state 1 to state 2 is adiabatic compression. In adiabatic compression, what is happening? Work in, heat in, work out, or heat out. What is the issue from the state 1 to state 2? For adiabatic compression. Anyone help me? What is happening? Is it heat in, heat release, or heat absorption, or work in, or work out? Come on.
Is it absorption?
Come again, sorry.
Absorb?
Absorb, heat absorption? No, remember the adiabatic compression. I will give you another example here. Adiabatic compression, 4-1 in this case. Can you guess this one? Adiabatic compression from 4-1. This is equal to work in, right? So it's not heat absorption, but work is coming to the system. This is work in. Okay. Now let's try for the second one. From 0.2 to 0.3. From 0.2 to 0.3. Heat insertion, increment in pressure, constant volume. What is the status in this case? Heat in, heat out, or work out? You can see from here, right? So heat is coming into the system. Okay, now help me again from 0.3 to 0.4. This adiabatic expansion. What would be the status?
Workout.
Yes, good. Thank you very much. Work out. And the last one, 0.4 to 0.1.
Heat out, sir.
Yes, hit out. Good. Okay. Please be aware because not only in the quiz, during the exam, there will be a lot of question regarding with this one. In fact, not only in PV diagram, you should be able to draw in any kind of diagram like PT diagram or pH diagram or in fact TS diagram and HS diagram. The entropy we will discuss after this. S is entropy. Okay, there is the Otto cycle, the gasoline motor. Now let's check for diesel cycle. Adiabatic compression. This is 0.1 to 0.2. What would be the status? Work in, work out, hit in or hit out? Come on guys, help me. It's the same as the previous example. Adiabatic compression, it means?
Work in.
Good. Thank you. Share. Now, there is a mistake in this sentence. Heat insertion, increment in pressure. If you check from the diagram, what is the status? Constant volume or constant pressure?
Constant pressure.
Good. So this should be replaced like this. And the status is heat in. This is 0.2 to 0.3. Okay, so the rest should be simple from 0.3 to 0.4. This is workout. And 0.4 to 0.1. This is heat out. Okay. Any question up to this point? If not, try to compare between Otto cycle and diesel cycle. Which step is different? Is it 1.1 to 0.2 or 0.2 to 0.3 or 0.3 to 0.4 or the last one, 0.4 to 0.1? Only one step is different. Can you guess which one is that?
0.2 to 3.
Okay, good. The difference is only this one, 0.2 to 0.3. When you use Otto cycle in gasoline engine, the principle is based on isometric or isochoric, isometric process. In diesel engine, they use isobaric. Based on this principle, they can optimize the engine. That's why in Otto cycle, it requires spark plug, ignition plug, to ignite the fluids, in this case, fuel plus air with a certain ratio, so it can explode and give expansion. On the other hand, for diesel engine, the system is based on isobaric. So after adiabatic compression, followed by isobaric condition. They try to reach what's so-called by flash point. That's why in diesel engine, we don't need spark plug, we don't need ignition. because diesel oil at a certain pressure will auto-ignite. That is the basic principle between these two. Consequently, if you want to go in much higher RPM, it will be better to have Otto cycle because of this similar condition between heat insertion and heat release, both using isometric condition. So it's good for high-speed car. Normally, when you check the engine based on Otto cycle, the top speed is relatively much higher compared with diesel engine. On the other hand, the advantage of diesel engine, it should have higher torque. So heavy duty car like truck, bus, it should be based on diesel engine. Because when the heat insertion occur, it will absorb extra energy. So the adiabatic expansion will be much longer. The work that can be released is much longer, so it can give higher torque. That's why heavy duty vehicle is very suitable for this purpose. Unfortunately, because there is a different step between heat insertion and heat release, when they try to push in higher RPM, it's not as smooth as Otto cycle. So most of the time, the top speed for diesel engine is not as high as Otto engine or gasoline motor. Okay, I hope now you can understand the difference between Otto cycle and diesel cycle, how it works, and how can you compare with the reality, how to calculate the efficiency. Use the same principle as Carnot cycle. Remember that the efficiency is equal to work net per heat in, both for Otto cycle and also diesel cycle. Remember, the work net would be different because only one step different, it can affect the whole thermodynamic process. Okay, up to this point, any question? Before we entering the entropy, I will give the opportunity to Pak Sanggono to explain additional information regarding with this system. Because later on, we will discuss also specific for several types of heat engine as well as several types of heat pump. But this is the basic principle, so you can be relatively easier to understand how to draw in PT diagram, pH diagram, and so on. Okay, for example, like Pak Sanggono mentioned in the last class, remember the pH diagram, pressure and enthalpy diagram with the dome like this for water and methane and also propane. There is an isothermal temperature, isothermal curve following this shape, and you need to draw for Carnot cycle in this system. It's also possible to draw in all kind of Muller diagram. It can be PV diagram, PT diagram, or pH diagram. For example, in Otto cycle, For example, in this Carnot cycle, let's draw it in PT diagram. So pressure and temperature instead of pressure and volume. Point 1 is high temperature, and then following high temperature to heat absorption. So the pressure is decreasing, but at a constant temperature. So this is point 1 and point 2. Oh, no, sorry, my mistake. I should write a little bit to the right. Point 1 to point 2. Why it is straight? Because this is isothermal process. Point 1 to point 2 is isothermal process. Okay. From point 2 to point 3, adiabatic expansion. In PT diagram for adiabatic expansion, you have to draw it in a curve with decrease of pressure. Like this, point 2 to point 3. Point 3 to point 4 is isothermal heat release. Oh, sorry. I will draw again. Point 1 to point 2 is point 1 to point 2 isothermal heat absorption, adiabatic expansion, heat release. Oh yeah, let's go. Point 1, point 2, point 3, point 4, then again point 1. Point 1, point 2, point 3, and then return to point 1. 1 and 2 is isothermal process. That's why T1 is equal to T2. In this case, T1 is equal to T2. Similarly, in this case, this is 3, T3 is equal to T4. Okay, so at least you can draw with a different type of diagram. Okay, any question? Now, tomorrow we will discuss more about this, but maybe Pak Sanggono, you want to add something, Pak?
Yes, I would like to share the screen just to add the information from Pak Hardev. This is the curve of the Carnot cycle. Sometimes it is written as QH, that is the hot temperature. This is the temperature. Sometimes it is written as TH, sometimes it is written as T2, or sometimes it is written as T1. Okay, so don't get confused. That's the point. And the same thing over here, we have the different temperature. And then in some of the books, it is not identified as expansion. Like Pak Hardev told you earlier that it is just at isothermal, the same temperature, and then it is absorption of energy to the system. Okay, but sometimes it is specifically it is written as isothermal expansion. Okay, so if it is not written as expansion, you have to understand that there is a change of the volume, then it is expansion or compression, things like that. And then this is a cycle of the Carnot. In the real world, it is like inside the piston, there is a combustion of the fuel with the oxygen. The question is, isn't it the combustion is inside the system? Why there is a Q passing the temperature line over here? Okay, it is just an illustration actually that Q is inside the system, but it enriched the energy to the system. Therefore, it is written as crossing the line over here. But the actual condition is that the fuel is inside the piston. Over here, we have the Q at cool temperature. It is passing because at higher temperature, there is a heat release from inside the engine into the environment. Yeah, okay. Up to this point, are there any questions regarding the Carnot cycle? This is an important one. Okay, if there is no question, I would like to go quickly to check where we are right now. This is the course content of the thermodynamics. The first week, second week, third week. We are now on the fourth week. So you have learned about the internal energy, the enthalpy, the specific heat, delta H, the latent heat of vaporization, condensation, this is specific heat. And then I think we haven't gone through the heat of reaction, but we will do that later. And then today you learn about the Carnot cycle. Later, Pak Hardev will go through the entropy definition. But you have done the entropy actually. You have been able to read the table and the diagram of the thermodynamic of the steam diagram last time. You remember there was UHS, okay? And then next week, it is supposed to be the week 5. It is about the Gibbs free energy. And then there will be the modular exam number 1 or midterm examination after the week number 6. After that, it is written over here, there is equation of state. It is for the gas equation of state, but it is likely that this agenda that is supposed to be on the 8th week, it will be moved into somewhere maybe in this week or next week. So it will be part of the first exam for the equation of state. Okay, and then the rest will go to the second midterm examination, second examination. Okay, I think that's what I need to add. Oh yeah, the other one, you need to be able to interchangeably make PV or pressure, temperature, or volume, pressure. Although it is unusual, but you need to be able to do it. And then remember, thermodynamics is about PVT, pressure, volume, and temperature. Those are the variables that can be measured. And then the calculated variables is the enthalpy, H, or the entropy later. So there might be a curve of this is enthalpy versus temperature, or enthalpy versus pressure, or entropy versus temperature. So it can be interchangeable. Okay.